Hi folks, my name's Scott Morrow and I'm the Numeracy Development Officer for South Ayrshire. Today's session focuses on developing a conceptual understanding of maths and the importance of teaching for understanding. I originally delivered this session at the Scottish Maths Conference on Saturday the 5th of March, but I've been asked to re-record it. There is a myth that exists in society that there is such a thing as a maths brain, that some of us are predisposed to succeed in maths and the rest of us don't and will never have an aptitude for maths. It's been scientifically proven that this is untrue and that every one of us has the ability to reason mathematically, to understand maths, to make mathematical decisions and apply this understanding to the world around us. A few years ago I was contacted by an old school friend because her son was struggling with maths and found himself in the bottom group in primary 3. The first time I met Scott, I asked him, if you have 9 sweets and I have 6 sweets, how many sweets do we have altogether? I said he could use any of the resources I'd brought along to help work it out, but he picked up a pencil and proceeded to write a 9 at the top, 6 underneath, addition sign, 2 lines, then he turned to look at me and said, I don't know what to do now. We put the pencil away and spent the rest of the session solving problems using counters and tens frames, neither of which he was using in school. I spent 1 hour a week with him, and at the end of the 4th session I asked him, Scott, if I had £235 and you had £328, how much would we have altogether? I expected him to show me using the resources or record us thinking in a number line, but instead he just thought for a minute and gave me the correct answer. When I asked how he worked it out, he explained that he started at 235 and added 300 to begin with to get to 535. Then he added 20 to get to 555. Then he added 5 to get to 560. And finally he added the remaining £3 to get to 563. The journey through school for children like Scott is fairly typical. Bottom group in primary 3, then remains there throughout 4, 5, 6 and 7. He then goes on to secondary school where he continues to struggle and never sees a national 5 or higher paper. Scott was and continues to be highly capable of achieving in maths. He just didn't get it the way he was being taught. I often ask children what word they associate most with maths, and amongst other responses, some of which I probably shouldn't repeat, the most common is numbers. Now, I'm not saying that maths isn't about numbers, but numbers on their own are pretty meaningless. We need to attach them to things to make sense of them. For me, maths is all about understanding relationships, whether it's part-part whole, comparison, multi-part, multiplication and division, or a combination of these, or fractional. The ability to analyse and visualise the relationship within a problem allows us to make informed decisions about how to go about solving it. These relationships are consistent throughout the levels and across mathematical contexts. Measurement, money, time, etc. As we progress, we are able to tackle more complex relationships involving larger values or fractions in a wider range of contexts. A pupil is asked to perform the following calculations. How confidently can you assess their understanding of each concept? How many of our pupils are able to perform these processes without actually understanding what they're doing? Is it important to understand so long as they're getting the correct answers? How useful is a jotter full of these? When I was at school, I was taught to do maths. I could perform the processes, I could get the right answers, I could perform well on a test. But if I'm honest, I didn't understand why I was doing a lot of it. Some people might be able to tell you that when you divide by a fraction, you invert it and multiply. Or they might be able to go through the process of factorising a trinomial. But how many understand what they're doing or why they're doing it? Each concept in maths is related. When we actually understand these concepts rather than just relying on memory, we can make connections, build a strong foundation, achieve new learning and progress to the next level. When maths is a series of memorised processes, all pupils will hit the wall. For Scott, it was very early in his maths journey. When I was at school, I thought I was good at maths. I realise now that while I could produce the right answers, I didn't really understand it. I got my higher, but when I started 6-year studies, I had no idea it was the same subject and gave up after a few weeks. If I'd sat that higher months later without studying, I would have certainly failed because I relied heavily on memorising processes I've been taught to do. I had no foundation. What does it mean to be numerate? Being numerate means being able to reason with numbers and other mathematical concepts and to apply these in a range of contexts and to solve a variety of problems. Being numerate is as much about thinking and reasoning logically as about doing sums. I disagree slightly and say that it has everything to do with reasoning logically and very little to do with being able to just do sums. Take a look at how 3 children solved the same problem. What was each child thinking? What issues do these solutions raise? You might want to pause the video for a few minutes to look at these. Pupil A understands that we don't need to start by subtracting the ones first. They've taken away 30 to begin with to get to 26. Then rather than trying to take all 8 away at once, they've taken away 6 to get to 20, then the remaining 2 to get an answer of 18. Pupil B has demonstrated an understanding of negative numbers. We tell pupils you can't take away 8 from 6, but of course we can. It's negative 2. So they've taken away the 8 from the 6, then the 30 from the 50 to get 20. Then they've added the 20 and the negative 2 to get 18. Pupil C understands that we don't have to subtract at all. They've found the difference by counting on from 38 up to 56. They've counted on 2 to get to 20, then 16 to get to 56, so they've counted on a total of 18. Each of these pupils has demonstrated a deeper level of understanding than they would display by simply performing the standard algorithm. The problem is that they have no idea how to articulate their thinking other than trying to shoehorn it into the process they've been taught in class. We need to equip pupils with the ability to articulate their thinking in a meaningful way. How might a child solve the following problem? I start with 5 sweets, I get 7 more sweets. How many sweets do I have now? If I presented this problem to a primary 2 class, for example, I'd like to think that given resources and time to work through it, they could all come up with the correct answer of 12. However, their understanding and progress can't be assessed by their ability to get the answer, but rather how they're actually solving it. The first child might count out 5 sweets, then 7 sweets, then count all of the sweets. They're counting from 1. The next child might put out 5 sweets, then 7 sweets, but rather than counting them all again, might say to themselves, I know I've got 5 there, and count on from the 5 to get up to 12. The next child might decide that they don't need to count on 1 at a time, but instead add 5 to get to 10, then the remaining 2. They're counting on, but more efficiently by bridging a 10 and performing the calculation in 2 steps rather than 7. The next child might decide to start at 7 and count on 5 rather than the reverse, demonstrating an understanding of the commutative law. And the next child might decide to take 1 from 7, add it to the 5 because they know double 6, demonstrating their ability to transform both numbers. Very often we make assessments on a learner's progress based on their ability to get correct answers. But in order to truly assess their progress, we need to get inside their heads to see how they're working it out. What strategy are they using? How efficiently are they applying that strategy? Because it's our job to support them develop a range of strategies and develop that efficiency. A few years ago, I was asked to support a girl in 2nd year who was struggling with fractions. When I met her initially, I asked her, if I've got 2 3/4 pizzas and you've got 1 1/4 pizzas, how many pizzas do we have altogether? I offered her a range of resources to work with, fraction cards, post-its, fraction wall, etc. Her response was to tell me there's only one way you're allowed to work this problem out. This was her working. She told me you had to start by multiplying 2 by 4 and adding the 3 to get 11 and write this at the top, then 4 underneath. I asked her why. I don't know. I asked her what that was. 11 over 4 was her response. I asked her what that meant. I don't know. She had no idea that she just converted the 2 whole pizzas into quarters to get 11 quarters altogether. Then she did the same with the 1 1/4, multiplying the 1 by the 4 and adding the 1 to get 5 over 4 as she put it. Then she told me she had to draw a smiley face and a kiss. Why do you do that? I don't know. She then explained that you multiply the 11 by the 4 to get 44, and you write that at the top. Then you multiply the 4 by the 4 to get 16, and write that underneath. Then she multiplied 4 by 5 to get 20, and 4 by 4 to get 16 again. Why do you do that? I don't know. She then told me that you add the numbers at the top to get 64, but you don't add the numbers at the bottom. That just stays 16. Why is that? I don't know. Okay, let's go back to the question. If I have 2 3/4 pizzas and you've got 1 1/4 pizzas, how many pizzas do we have altogether? She looked down at her working and said, 64 over 16. What does that mean? I have no idea. So we put that to the side and I gave her a pile of post-its. I asked her to quarter a post-it. She ripped it into 4 uneven parts and handed them to me. She had no idea that quarters had to be equal in size, if not shape. Once we'd explored fractions for a while using the post-its, making halves, making quarters by halving the halves, I asked her to have another go. She gave me 2 post-its for the 2 whole pizzas and 1 to herself. Then she took out another and said, I'll need to quarter this and take 3 of those quarters. As she was ripping out the extra quarter that she wouldn't need, she said, oh, I can use this for my quarter pizza. Then she looked at what she laid out and said, we've got 4 pizzas altogether. There's something very wrong with a process when I ask a child to add 2 3/4 pizzas and 1 1/4 pizzas and they respond with 64 over 16. That process is actively preventing her develop an understanding of fractions, an understanding she's clearly more than capable of when she's taught appropriately. A child was asked, if a baby was born in 1998, how old were they on their birthday in 2001? The response was 3. The same child was asked, what is 2001 take away 1998? This was their response. What were they thinking? Again, you may wish to pause to consider this. The first answer demonstrates their ability to make sense of the problem and to apply a suitable strategy. They simply counted on 3 from 1998 to get to 2001. The second problem wasn't presented in a context. They simply viewed it as a calculation they had to perform. No mathematical reasoning involved, no decisions to take. I just have to take away that number from that number. The mistake you see here is a common one because they're simply trying to regurgitate a process they've been taught and have failed to memorise it correctly. They've said 1 take away 8 I can't do, so they've simply reversed the figures and take away 1 from 8 because they've failed to attach any meaning to the calculation whatsoever. In order to solve any mathematical problem, there are 3 key elements. The first thing we need to do is analyse it in order to make sense of the problem. Once we actually understand what we're being asked, we can make a decision about how to solve the problem. And as we're solving it, we can apply our understanding of number. When we give pupils calculations to solve, we're already telling them the process to perform. We're not asking them to analyse anything or apply any kind of reasoning. Yes, they can choose between different strategies, but we're already telling them, I want you to add these numbers, or I want you to take that number away from this number. It's really important that we develop their decision making and ability to analyse problems rather than instruct them to perform a calculation. By setting the problem in a context, we allow pupils to make sense of number and make mathematical decisions. How many times have you set a maths problem? A pupil works out the correct answer but can't explain what they actually did. I just got the answer, I just did it in my head. It's essential that pupils are able to articulate the steps that they're performing in their heads. Over time, pupils often develop a reluctance to use manipulatives. What causes this attitude? When manipulatives aren't readily available or available if you need them, pupils see them as a sign of weakness. If I have to use those resources, I'm sending a message to everyone around me that I'm struggling with this. So pupils avoid them if they can. Manipulatives support all learners develop a deeper understanding of mathematical concepts at all levels. They empower learners to communicate the processes they're going through when solving a problem and support them to organise their own thoughts. They also support teachers make an accurate assessment of a learner's thinking and progress. I used this activity in a class a few weeks ago. Once I'd set the problem, told the children that they had to explain to each other how they were working it out, but weren't allowed to talk to each other, in order that they had to use those manipulatives to communicate their thoughts, one boy stuck up his hand looking confused and said, "Well, you've not told us if we need to add or take away." I never want to tell them they have to add or take away. His experience of maths has been being told what calculation to perform, working through pages in a textbook that tell him at the top of the page what process he needs to perform. He's never needed to analyse a problem, leading to him finding difficulty in making a simple mathematical decision. Even those word problems we find in those textbooks, do we really need to analyse them? Or can we just look at the top of the page, see that, well, today we're multiplying, so I'll just multiply the numbers in the problem. And contextualised problems doesn't mean it has to be a written word problem. Consider the questions that we can ask from this simple visual. So reading ability should not be a barrier to children developing understanding of maths. Even a worded problem can be talked about, shared with the class, discussed. It doesn't have to be set in front of the pupils for them to read individually. Our ability to reason mathematically and make mathematical decisions is innate. A young child won't be able to count the sweets in either of these piles, but they can work out which pile they'd rather have. They're going to go for the bigger pile. Our job as teachers is to continue to nurture this innate ability to make mathematical decisions. I give this problem to a lot of classes, and to be honest, it's not the right answer that interests me, it's more the wrong answer that some pupils make. I gave this question to a primary 6 class with 30 pupils, and out of 30 of them, 27 got the same wrong answer. So the correct answer of 25 isn't important. What's important is, what was that wrong answer, and why did they all make that same mistake? I can analyse this problem using a bar. Here's a bar that represents the whole amount, and in this case the whole amount is the donuts that Homer's got to start with. What does he do with those donuts? Well, he shares some with his colleague, and he keeps some. So how many parts am I going to split this bar into? I'm going to split it into 2 parts. Those that he shares and those that he's left with. Now we can put in the numbers we know. We know that he gave 5 donuts to his colleague and that he started with 30. What we're trying to work out here is how many donuts he was left with. I could solve this in different ways, but for this particular problem, I find it easiest to take away 5 donuts from the 30. That leaves me with the 25 donuts. But what was that mistake that they all made? The wrong answer that 27 children got was 6 donuts. Where does that 6 donuts come from? Well, what they did in this particular example was they divided. And why did they divide? Because they told me they saw that word shares. Now, shares can mean divide. If the question was, Homer had 30 donuts, which he shared between 5 of his work colleagues or 5 friends, then yes, we would divide those 30 donuts between 5. But that's not what's happening here. In the early part of my career, when I was teaching problem solving, I used RUCSAC. Read, underline, calculate, solve, answer, then check. I told children that if they saw a particular word, then they had to perform a particular calculation. So if they saw the word share, they would divide. If they saw the word altogether, they would add. But I might say, Scott and Finn have got £30 altogether. Scott's got £23. How much money does Finn have? Now that problem uses the word altogether, but we're not adding the numbers in the problem in order to find the answer. The strategy of highlighting keywords when problem solving actively discourages learners from reasoning about the structure of the problem itself. That mathematical language that we find in problems does not dictate what calculation to perform. it gives us an insight into the relationship within the problem itself. Once we're able to visualise that relationship, we can make sense of it and we can make informed decisions. Have a look at the following problem. Bart has 28 Lego figures altogether. He has 5 more Star Wars figures than Marvel figures, 4 fewer Harry Potter figures than Marvel figures. How many of each does he have? How might pupils typically approach this? Would some give up straight away? It's important to develop resilience through problem solving. It's okay not to get the right answer, to make mistakes, to struggle, to take time over it. You might want to pause the video for a couple of minutes to have a look at this yourself. Learners who focus on numbers tend to either give up or use guess, check and improve as a strategy. The key to solving this problem is through visualising what we know about the relationship between each set of figures. We don't actually have any information about the number of Star Wars, Marvel or Harry Potter figures, but what we do have is information about the relationship between them. So to start with, I know that Bart's got more Star Wars figures than Marvel figures, and he's got fewer Harry Potter figures than Marvel figures. So I can put them in the correct order. Now, I don't know how many Harry Potter figures he's got, I just know he's got some. So we can draw a bar to represent that unknown quantity. Now, however many Harry Potter figures he's got 4 more Marvel figures. So we can represent that with the same bar as Harry Potter, plus an extra 4 figures. And then we know that there are 5 more Star Wars figures than Marvel figures. So we can draw exactly what he's got for Marvel, which is the unknown quantity, the 4 extra figures, but then we can add an extra 5 figures. What we've got now is a visual of the relationship between each of those sets of figures. And we know that altogether there are 28 figures. Now you can see that we've already accounted for 13 of those figures. So we can set those aside a little minute. Let's just take them away. And when we do that, we're left with 15 figures that must be evenly shared between those 3 unknown quantities. So we can put 5 in each of those. And once we've done that, we can bring back the figures that we already knew about, meaning there are 5 Harry Potter figures, there are 9 Marvel figures, and there are 14 Star Wars figures. How would you solve the following problem? Bart goes into a shop with £20. He buys sweets for 15p. How much does he have left? Let's consider what's the most efficient strategy for this. If I was going to solve this, I would start at the £20 and I would simply take away that 15p. I might take away 10p to get down to £19.90 and then take away 5p to get down to £19.85. You might do that using a different strategy. Now let's consider the same problem, but let's change the values around a little. Bart goes into a shop with £20. He buys sweets for £19.85. How much does he have left? Now this time, let's try subtraction again. Even if I do that fairly efficiently, I could start at £20. I might take away £10 to get to £10. I might then take away £9 to get to £1. Then take away 80p to get to 20p. Then take away 5p to get down to 15p again. Now you can see here it's a pretty inefficient strategy to solve this problem. So what would be more efficient? I could start at £20 and count back to £19.85. So I might take away 10p to get down to £19.90 and then 5p to get £19.85. A much more efficient strategy to get my 15p change. Or, alternatively, I could have started at £19.85 and counted on to £20. And again, I could count on 5p to get to £19.90 and then 10p to get to £20. Of course, getting the same answer each time, however, we're making more effective decisions because we're using a more efficient strategy given this particular problem. Let's consider the following problem. A man had £2,135. He spends £1,787 on a new bike. How much does he have left? This is how I used to teach this. I'd write out an algorithm like this, and I would tell children, let's start by subtracting the units. 5 take away 7, I can't do. Of course we can, we would get -2, but let's get past that at the moment. So 5 take away 7, I can't do. I would go next door and I would borrow one of those 10s. Now, of course, I'm not borrowing a 10 because they're never getting it back. That leaves me with 2 10s. I'm going to exchange 2 10s for 10 1s, and now I've got 15 take away 7. And if I take 7 away from 15, I get an answer of 8. Then I'm going to subtract the 10s. Now, it's not very clear that actually that 2 represents 20 and that 8 represents 80. So here, what children might say is 2 take away 8, but of course it is 20 take away 80. Again, let's lie to the children and tell them we can't do that. So we're going to have to go next door again, borrow that 100, so we've got no hundreds there. I'm exchanging that for 10 10s. I've now got 12 10s. 12 10s take away 8 10s is 4 10s, and I can move on. 0 take away 7, again it's 0 hundreds, take away 700, but that's not clear from this algorithm. 0 take away 7, I can't do. So let's go next door and borrow one of those thousands, leaving 1000 there and exchanging 1000 for 10 hundreds. 10 hundreds take away 700s is 300, and then 1000 take away 1000 is 0. So I get an answer of £348. No wonder children struggle with the subtraction algorithm. It actively acts as a barrier to developing an understanding of place value. Children get completely lost with it, and it doesn't allow them to make connections to other concepts in maths. Here's how I would solve that problem. You might do it in a different way. I know that I'm just finding the difference between the £2,135 and the £1,787. So I would start at 1,787 and count on to 2,135. I could count on 13 to get to 1,800. Then I might count on 200 to get to 2,000. And then I could count on the 135 to get to 2,135. So what have I counted on altogether? I can just add up those jumps to get £348. Let's consider how important it is to develop conceptual understanding and how this impacts our ability to understand more complex concepts as we progress through school. Let's consider the relationship between multiplication and division. I often start by asking pupils what multiplication and division actually mean. Some tell me things like multiplication means times. Some can correctly perform a calculation. But do they truly understand these concepts and the relationship between them? It's often assumed that this is a two-way relationship, that multiplication and division are the opposite of each other. But let's consider this relationship visually. Let's say I've got 4 boxes of cakes with 5 cakes in each box to give me 20 altogether. There aren't just 2 possible unknowns here, but 3. We could make the whole amount the unknown and ask, how many cakes do I have altogether if I've got 4 boxes with 5 cakes in each? Or we could make the value of each part unknown and ask, I want to share 20 cakes between 4 boxes. How many will there be in each box? But I could also make the number of parts the unknown. I have 20 cakes. I want to put 5 in each box. How many boxes do I need? Children often obsess over getting the right answer because historically that's why they've received praise. I often tell them I have no interest in the correct answer. It's their ability to explain how they got there that's important. This is quite a nice activity to do with them because all the answers are already there. It's the questions they've got to come up with. Their ability to come up with appropriate questions gives us a greater insight into their understanding of the mathematical relationship. So can they come up with 3 different questions for the following relationship? There are 3 possible unknowns. The first might be to make the whole unknown. For example, Batman has 3 bags with 6 sweets in each. How many sweets does he have altogether? The second might be to make the value of each part unknown. For example, Batman shares 18 sweets equally between 3 bags. How many sweets will there be in each bag? And the third might be to make the number of parts unknown. For example, Batman has 18 sweets altogether. He wants to put them into bags of 6. How many bags will he need? Consider the following calculation. How many correct answers can you find for 27 divided by 4? I ask this question in a lot of classes and I get some strange looks, as you can imagine. I also get a lot of strange answers. It's a question that pupils typically struggle with. I also want you to consider what strategy would you use to solve this calculation and what determines your choice of strategy. We're going to revisit this in a minute or two, but before we do, let's consider the following. 12 players have to be divided into 3 teams. How many players will there be in each team? As I've said before, it's not the answer I'm looking for, but what pupils do with the counters or cubes I've supplied them with. The nature of the problem leads them to do something like this. Set out 3 teams, then share the players between the teams, either one at a time or maybe more efficiently by sharing out 2, 3 or even all 4 at a time, until they find that there are 4 players in each team. Then I ask them to divide 12 players into teams of 3. Again, the answer isn't really of interest, it's what they do with the counters that's important. The problem dictates that they don't know the number of teams, so sharing isn't an option here. Instead, they might take a group of 3 to make a team, then another, and another, and then another, until there are no players remaining. The first scenario led them naturally to sharing, whilst the second led them naturally to group the players. Let's return to 27 divided by 4, only this time let's set a context. 27 chocolate bars have to be shared equally between the 4 professors. How many chocolate bars should they each get? This time I'm going to draw a bar to represent the whole amount. I'm going to split it into 4 parts because I'm sharing the chocolate bars between the 4 professors, and then I can start to share them out. Now we could share them out one at a time, but here I've decided that I've got enough to give each of the professors 4 chocolate bars to start with, and then I can give them another 2 each. So pupils could rightly justify that each of the professors can get 6 bars of chocolate and there'll be 3 left over. Let's not use that abstract term remainder. Let's consider what to do with those 3 remaining bars of chocolate. Some pupils might correctly conclude that each professor could be given 6 bars and put the 3 extra bars back in the box. So 6 each and 3 spares is one possible answer to this problem. But we're dealing with chocolate bars here, so we could potentially break them into smaller parts. We could split each bar into quarters, giving us 12 quarters, which can then be shared evenly. So we've found another potential answer here. Let's consider an alternative context. This time we've got 27 Lego figures to be shared equally between the 4 professors. How many figures should they each get? But this time the context is dictating that we can't quarter a Lego figure, because nobody wants a broken figure. So there's only one potential outcome here. 6 figures each and 3 spare that we could put back in the box. What happens when instead of chocolate bars or Lego, we're sharing out money? £27 has to be shared equally between the 4 professors. How much money should they each get? This time it makes sense to give them £5 each, then £1 each. So once again, they've got 6 each, but this time it's pounds, and we've got £3 left over. The professors want their fair share, so instead of trying to quarter those coins or keep them as spares, we can exchange them. We can exchange them for 6 50p and give them a 50p each. Then we can exchange the pound that we're left with for 5 20p and give them a 20p each. And then we could exchange the remaining 20p for 4 5p. So this time we get an answer of £6.75. Finally, let's consider the following problem. 27 people need to get a taxi to the airport. A taxi holds 4 passengers. How many taxis should they order? The context dictates that we can't share this time because the number of taxis is the unknown. So what do? Well, we might begin by ordering a taxi and put 4 passengers inside. Then repeat this until we've filled 6 taxis and have 3 passengers left over. But those 3 passengers still need a taxi. So we need to order an extra taxi. So in this case, our answer is 7 taxis. Now, I could have asked how many full taxis will there be, to which the answer would obviously be 6. The underlying calculation for each of these problems was 27 divided by 4. However, it was the context that supported our decision making about how to solve each of them. The first 3 naturally led us to sharing, while the last led us to grouping. But not only did it support our decision making, the context allowed us to make decisions about what to do with that remainder, each time producing 4 different answers. By setting a context, we are nurturing pupils' ability to make informed decisions about how to go about solving, and allows them to make sense of what is otherwise just an abstract calculation. So let's consider how this understanding of sharing and grouping supports pupils' understanding of more complex concepts like dividing by a fraction. If my only understanding of division is sharing, then even when I contextualise the calculation, it doesn't make any sense. 2.5 pizzas shared between 1/4 of a person. What does that even mean? But if I understand grouping, what we're really asking is how many lots of 1/4 pizza can I get from 2.5 pizzas? So how many portions can we get? There's our bars to represent the 2.5 pizzas, and I can divide them into quarter portions to get 10 quarters in total. What about 5 divided by 2/3? If I invert and multiply, I get an answer of 15 halves, or 7.5. But where does the half come from if I start dividing by thirds? 12 divided by 3 can be thought of as how many lots of 3 can I get from 12, just like we saw with the teams example before. So how many lots of 2/3 can I get out of 5? Let's consider the following contextualised problem. A glass holds 2/3 of a carton of orange juice. How many glasses can be poured from 5 cartons? Let's start with 5 bars to represent the 5 cartons. A glass holds 2/3 of a carton, so we'll need to split our cartons into thirds. A full glass holds 2 of these thirds, so we can represent a glass with 2 of those parts. We can pour out the cartons 2/3 at a time to fill a glass at a time until we've filled 7 glasses and we're left with 1/3 of a carton. What happens when we pour this last third into an 8th glass? It fills half of that glass. The third relates to a carton. The resultant half relates to a glass. That's how we end up with halves in our answer when we start dividing by thirds. The context allows us to make sense of it. So let's not give students abstract calculations that require them to regurgitate a memorised process when we can develop their understanding and allow them to make connections to other concepts. So what does progression in maths actually look like? Traditionally, we tend to compartmentalise concepts, teaching them explicitly. Place value, addition, subtraction, measurement, money, and so on. But all mathematical concepts are interlinked, and the relationships I referred to earlier are consistent across concepts and levels. By teaching concepts discretely, we often develop gaps of understanding because pupils fail to make connections, and because of the time it takes to revisit a concept. Some of these concepts are only revisited once a year. I see progression in maths like a whirlwind. Starting at the bottom, we might use a particular strategy for addition, for example. As we progress, we develop more strategies. We make connections between concepts by continually working in a cycle, revisiting concepts, making connections, developing and improving our decision making, the efficiency with which we apply strategies. We widen the range of contexts within which we can apply our understanding from tangible, cookies, stickers, bags of sweets, to the intangible, distances or time periods. And our mathematical reasoning continues to develop, allowing us to cope with increasingly complex problems. To summarise the key messages from today's session, It's important that we develop conceptual understanding over procedural knowledge, because it's that understanding that allows us to make connections and make greater progress in maths. Speed of recall is not an effective measure of a pupil's ability in maths. Yes, as we develop understanding, our speed will increase, but when speed is viewed by pupils as a measure of their success, it becomes a barrier and develops maths anxiety. The focus should be on how rather than the result. We want to encourage children to make their thinking visible. We want to develop a mistake-friendly classroom environment where children are encouraged to make mistakes in order that we learn from those mistakes. Intervention should be consistent with classroom practice. So the extra support that we give to some children should reaffirm what's happening in class. It's vital that practitioners understand how progressive concepts are linked. As a primary 2 teacher, I'm not going to be teaching division by a fraction, but my understanding of mathematical pedagogy will support my practice in order that we are developing concepts that lead to greater understanding further down the line. And true progress in maths is about developing the ability to make sense of a problem, to apply that mathematical reasoning, to choose increasingly effective strategies and improve our decision making, to apply those strategies with increasing efficiency and be able to articulate and justify our thinking. If you'd like to get in touch, you can email me at scott.morrow@southayrshire.gov.uk. You can follow me on Twitter @ScottMorrowSA, and you can find a series of first and second level lessons that develop conceptual understanding of maths at my YouTube channel. Thanks for taking the time to watch this video.